Good morning. We are now going to work out a few numerical examples corresponding to the portions we covered so far, which is actually controlled rectifier, diode rectifier, and so on. So I'm going to focus more on controlled rectifiers. So the first problem statement goes as follows. So this is a single phase half wave controlled rectifier is having a supply voltage of single phase 240 volts 50 hertz. It is feeding a resistance of 5 ohm. Calculate the average voltage and average current through the load. What is the power delivered to the load? So this is what is being asked. One thing I would like to underline repeatedly is when you are given 240 volts 50 hertz, 240 volts is the RMS value, root mean square value, unless it is mentioned otherwise. Always in three-phase case, line voltage RMS is given. Line voltage RMS will be given. And similarly, in single-phase case, whatever is line to neutral voltage RMS value will be given. So this is generally should be taken as the given value unless it is mentioned otherwise. So let us try to look at the solution for this case. So what is given is, it is a single phase controlled half wave rectifier. So if let us say this is the voltage source, which is 240 volts, 50 hertz, single phase, and we are having a controlled rectifier, which means it has to be an SCR. So what we are given is an SCR. And we are looking at a resistance of 5 ohms being fed. Now, what we need to calculate is what is the load voltage and what is the load current that is flowing, average value, and what is the power. These are the three things that are being asked. So let me start with drawing the waveform. So let us say this is our input voltage. So this is omega t, and we are looking at this as Vs. So the peak value of the voltage will be 240 times root 2 volts. That is going to be the voltage value. Now, of course, firing angle needs to be given. So let us say firing angle. Let us write the firing angle. So here, if alpha equal to 30 degrees. So firing angle is given as 30 degrees. So let us say this is the point at which alpha is equal to 30 degrees. So because it is the resistive load, we will get this entire thing coming up as the output voltage. So it will be from alpha to pi. That is what is showing up as the output voltage. Now, as far as the current is concerned, we will have, let me draw the current as well. So we are going to have the current starting from 30 degrees and it will come up like this. So this is going to be whatever is Vs divided by R. That is going to be the current and it will only start from alpha and it will go until pi. That's all. So this is going to be the current. So this is I load. And this is V load. So this is the way it is going to be. So let us first of all derive this again. So we can say V load average is going to be starting from alpha and it will go until pi. And we are going to have Vm sine omega t d omega t. And it has to be averaged over 2 pi. So this is going to be Vm, which is actually 240 times root 2. So Vm, the maximum voltage, peak voltage is going to be 240 times root 2 volts. So 240 times root 2 divided by 2 pi multiplied by sine omega t. When you integrate, it is going to be minus cos. So I can write this as cos omega t with the limit of alpha at the top and pi at the bottom because the minus sign has been removed. So I can write this as 240 times root 2 divided by 2 pi multiplied by cos alpha minus minus 1. So it is 1 plus cos alpha. So this is going to be the overall voltage what we get. And cos alpha is cos 30. So cos 30 is generally root 3 by 2. So which is actually 0.866. So I can write this as 1.866 multiplied by 240 times root 2 divided by 2 pi. So this comes out to be 100.8 volts. Please verify the calculation. So this is going to be 100.8 volts. So we are going to have now I load average is going to be whatever is V load average divided by R. And R is given to be 5 ohms here. So this is going to be 100.8 divided by 5, which will come out to be 20.16 ampere. And the power delivered or power dissipated in R is going to be either I square times R or V average square divided by R. Either way is fine. And this comes out to be 2032 watts. So which is actually 20.16 whole square multiplied by 5. Or I can also write this as 100.8 square divided by 5. So this is going to be the wattage which is coming across the resistance. Okay. So this is one problem that we have worked out now. One numerical example on half wave controlled rectifier. Okay. So let us now try to go on to second numerical example. So you can say numerical example on one phase controlled rectifier. So this is a single phase. So let me probably write this as explicitly single phase controlled rectifier. So let us now look at the problem statement corresponding to single phase controlled rectifier. So a single phase fully controlled rectifier operating at a firing angle of 22 degrees is fed by a 240 volts 50 hertz supply. Of course, single phase 240 volts 50 hertz supply. It is charging 180 volts 12 ampere hour battery having an internal resistance of 0.45 ohm. If the maximum current taken in by the battery is 7 ampere, what should be the current limiting resistance to be connected in series with the battery? Assuming that a large inductance is also connected to make the current ripple free. Ripple free means we are going to have almost a steady current. So the current will be literally steady. It cannot be having any variation like this. We are going to have a steady current. That's what it means when we talk about ripple free current. Okay. So the first thing that is asked is what should be the current limiting resistance value. The second thing that is being asked is calculate the average load voltage. So what is the average load voltage and average or the power delivered to the battery, and the third thing is time taken for charging the battery fully from completely discharged condition. Also, draw the waveforms of supply voltage, supply current, load voltage, voltage and load current. So this is the numerical example that we are going to work out now. So let me start by drawing the circuit diagram. So the circuit diagram is somewhat like this. I'm going to have one SCR here, second SCR here, and third SCR here, and fourth SCR here. That's why it is fully controlled rectifier when I'm going to have four SCRs connected like this. And I will have a resistance, I'll have an inductance, and the battery. So this is the circuit diagram what I have. And I'm going to look at this as the supply voltage. So this is 240 volts, 50 hertz, single phase AC. And I'm having this device as, say, T1, this as T4, this as T3, this as T2, and this is the external resistance we are connecting. This is L, and this is going to be 180 volts and 12 ampere hour battery. And what is the current that is flowing is average current of 7 amperes, not anything more than that. So what is being asked is what should be the resistance value if I want to limit the average current to 7 ampere. So I should also write maximum average current. We don't want to look at instantaneous current. Maximum average current taken in by the battery is 7 amperes. So let me first of all draw the waveform so that, whatever is asked in subdivision 4, let us first of all fulfill that. So I'm going to have the voltage, supply voltage somewhat like this. And we are looking at a firing angle of 22 degrees. So this is going to be, say, 22 degrees. I'm just writing like this, that this is 22 degrees. So when I look at the rectified voltage or during the negative half cycle, this is how it will be. Again, let me show this is pi plus 22 or 180 plus 22 degrees. It will be 202 degrees. So let us say this is 202 degrees. And this is pi. So what we are looking at is the voltage. If I assume continuous conduction, the voltage that comes out on the output side is going to be somewhat like this. And again, this will follow this. So this is going to be the voltage. What I see as the voltage is somewhat like this. This is how the voltage will be. So this is V load, and whatever I have drawn in blue color, that is V supply. If I may call this as Vs, this is what is Vs and this is V load. So I should be able to calculate V load average value as from here, from let us say 22 degrees until 202 degrees, or I can say in general alpha to pi plus alpha. I can simply write this as alpha to pi plus alpha 1 divided by pi Vm sine omega t d omega t, where Vm is equal to 240 times root 2 volts. So we had already derived this, if you may recall. This will be Vm divided by pi cos alpha minus cos of pi plus alpha. This is what we derived, and we said that this will be 2 Vm divided by pi cos alpha. That's what we wrote earlier, if you may recall. So I can remove this, doesn't matter. So this is going to be 2 Vm divided by pi cos alpha. So I can write this as 2 multiplied by 240 root 2 divided by pi and cos of 22 degrees. So this comes out to be 200.335 volts. Now, whatever I'm looking at as the resistance, that is the one which is limiting the current. So I should be able to write I load average, which should be only 7 amperes. This should be equal to 200.335 minus whatever is the battery voltage, which is 180 volts, divided by the resistance, plus whatever is the internal resistance of the battery. Please remember, the current, whatever is flowing through this particular branch, whatever is the voltage drop across the inductance will be literally zero on an average basis, because L di by dt, when di is increasing, when current is increasing, L di by dt during that portion will be equal to L di by dt when di by dt is negative or the current is decreasing. It will be averaging out to zero. That's why we are not taking any inductance drop at all. This is literally zero. So this is the equation which will actually make sure that the current is limited to 7 ampere. So what we get is R plus R internal will be equal to 20.335. That is the voltage that is available, divided by 7 amperes of current. So that comes out to be 2.9 ohm. And internal resistance is given to be 0.45 ohm. So 2.9 minus 0.45 ohm, which is going to be R. This is the current limiting resistance. Current limiting resistance. What I need to connect externally. So that is equal to 2.45 ohm. So we have to connect the current limiting resistance of 2.45 ohms if I want to limit the average current to 7 ampere. Now what is being asked next is, what is the average load voltage, which we have already calculated, which is 200.335, power delivered to the battery, and time taken for charging the battery. So power delivered to the battery is whatever is the voltage of the battery multiplied by current taken in by the battery. Average current again. So average current taken in by the battery, we are limiting to 7 ampere. And voltage of the battery is 180. So 180 multiplied by 7. So that is 1260 watts. This is the power taken in by the battery, power delivered to the battery. But if you look at the power delivered by the rectifier, for example, the total voltage that is delivered by the rectifier is 200.335 multiplied by 7. So many watts will be delivered by the rectifier, out of which part of it is dissipated in the resistance here and part of it is dissipated in the internal resistance. So those are all wastage of power, but we can't help it. That is the way it is. Okay. Now, the last one is being asked, that is being asked is time taken for charging the battery fully from completely discharged condition. So if it is completely discharged and it has to be charged fully, the total ampere hour capacity of the battery is 12 ampere hour and what we are supplying is only 7 ampere. So this is going to be 12 divided by 7 hours. So this is the total time taken for charging the battery. Now let us try to draw rest of the waveform. Draw the waveforms of supply voltage, supply current, load voltage and load current. So we have already drawn supply voltage and load voltage. Those two are drawn. So if I draw the load voltage again explicitly, I should draw it as though from 22 degrees, it is going like this. And then it is again jumping up like this. And this is the way the load voltage is going to be. This is the load voltage. So if I try to draw the current, the battery voltage is 180 volts. The peak is 240 times root 2, which will be about 350 volts or something. So this is going to be about 350 volts. So you can say roughly our battery voltage will be half of this. So maybe battery voltage will be somewhere here. This will be the battery voltage. So when I actually fire the device, maybe the current would slightly come down and then it will start increasing and then it should come down from some point where Vm sin omega t, that is Vm sin omega t, which is Vs equal to Ri plus L di by dt plus V battery. This is the way I will have the governing equation. So Vs minus V battery minus Ri equal to 0. That is where the current will reach maximum. So the current will now come down like this. And then again, it should increase and come down like this. So this is the way we are going to have the current. This is going to be I load. But what is written is the current is ripple free. So approximately we can draw the current to be, if I say this is omega t, the current is going to be somewhat ripple free. So I can draw it like this. The current is somewhat like this. This is how the current is going to be. So this is I load. But I can say from here till this point, I'm going to have T1 and T4 conducting. And from here until this point, it is going to be T2 and T3 conducting. And whenever T1 and T2 are conducting, I am going to have the current exactly in the positive direction. So from here until here, the supply current will be exactly same as that of whatever is the current I'm observing on the load side. Whereas when T2 and T3 are conducting, the current is going to be exactly the opposite to that of the load side current. So this is going to be the supply current waveform if I try to look at it as what is IS. So this is going to be the supply current waveform. So we have drawn supply voltage, supply current, load voltage, load current. We have also shown which are the devices that are conducting at different intervals. So I can say from alpha to pi plus alpha, I will have T1 and T4 conducting. And from pi plus alpha to 2 pi plus alpha, I am going to have T2 and T3 conducting. These two are going to conduct. Instead of having all four as SCRs, if I am going to have two SCRs and two diodes in a single phase controlled rectifier, we call that as half controlled or semi-controlled rectifier. If I have two diodes and two SCRs, because I will have, if I just say that I'm going to have two of them as SCR and two of them as diodes, it is as good as not controlling one half of the rectifier. So that is definitely going to result in a different kind of waveform. It will not be the same as what we have seen for fully controlled rectifier. But because we are primarily concentrating on all the power converters that are needed for electric vehicle purpose, I am really not going into the details of half controlled or semi-controlled rectifier. So if you want to really learn about it, you might have to look at the hardcore power electronics course. So I'm not really getting into those details. The third problem that what we are going to look at, the third numerical example that we are going to look at is on three-phase fully controlled rectifier or full converter. That's what we are going to look at now. Okay, so the problem statement of this three-phase fully controlled converter is like this. A three-phase 440 volts, 50 hertz supply is connected to a three-phase full converter or fully controlled rectifier feeding a 300 volts 20 ampere hour battery. The average current is to be limited to 15 ampere. The battery voltage fluctuates between 275 volts and 300 volts when it is completely discharged / fully charged. Okay. Now, what is given further is that uh, the current limiting resistance totally available in the circuit is 2 ohms. Calculate the range of firing angles between which the converter is to be operated assuming that a large filter inductance is there in the circuit to make the current, the load current or battery current ripple free. Draw the waveforms of A phase supply voltage and supply current. Load voltage and load current. Specify which devices conduct at what interval. Okay. So this is what is the problem statement. Now let us look at the solution. So first of all, let me draw the 3-phase fully controlled rectifier or full converter. So these are the 6 devices we are looking at. So let me complete the circuit. And we have R, L, and the battery. And battery is given to be so this is VA, VB, VC, this is T1, this is T3, this is T5, this is T4, T6, and T2. So these are the thyristors that we have drawn. Now this is going to be 2 ohm resistance, and this is a large inductance, and this is going to be 300 volts and 20 ampere hour battery. And the current has to be limited to 15 ampere. That is what is given. Now the firing angle we need to calculate. So let me just draw the 3-phase voltages. So let me just draw the second phase somewhat like this. The second phase is here. And the third phase is going to be somewhat like this. So these are the 3 phases. Okay. Now, so this is the third phase. So VA, VB, and VC. These are the 3 phases. Now, what we are looking at is, we don't know the firing angle. This is the point where alpha is 0 degrees. And we are going to probably fire it at some point somewhere. We don't know. So let me assume maybe the firing is somewhere here. So we are going to have the waveforms in such a way. Previously what we drew, maybe we will have something like this as the voltage which is coming up. So I'm going to draw this as the voltage which is coming up at the DC side or load side. So if we are firing 1 here, 6 must be already conducting. So this will be VAB, this will be VAC. Please recall what we drew as the waveform. So this we said VAB, this is VAC, then this is BA, VBC, then VBA, VCA, and so on. This is what is the typical. So when we talk about 1, 2 conducting, 6 and 1 conducting VAB, 1, 2 conducting VAC, 2, 3 conducting VBC, 3, 4 conducting VBA, and so on. So the same thing, let me show here. So this is VAB, VAC, VBC, VBA, and this is going to be the next one. What we see here will be in all probability VB, VCA, and VCB. So this is the way the voltages are. Okay. So we will again tell about what are all the devices that are going to conduct. Here it will be 1 and 6. This will be 1 and 2. And this will be 2 and 3. This will be 3 and 4. This will be 4 and 5. And this will be 5 and 6. So let me show clearly the periods also where each of them conduct like this. So the devices that are conducting, we have marked them as well very clearly. So let us first of all try to write the expression corresponding to V load average. That is going to be, we derived this, if you may recall, this is from alpha pi by 6 plus alpha 2 pi by 6 plus pi by 3 plus alpha averaged over pi by 3. We wrote this as VAB d omega t, and VAB d omega t, we wrote this as VLM, whatever is the line voltage peak, sine of omega t plus pi by 6, because compared to VAB will be leading by 30 degrees. And we wrote this as pi by 6 plus alpha, and this is pi by 2 plus alpha. And this is going to be 3 by pi d omega t. And when we derived this, we got the expression, if you may recall again, that is three-phase. When we derived the expression, we got this as 3VLM divided by pi cos alpha. For the controlled rectifier, we got this as 3VLM by pi cos alpha. This is for diode rectifier, but when we looked at the three-phase fully controlled rectifier, we got this as 3VLM by pi cos alpha in one of the previous lectures. So we can write this as 3VLM divided by pi cos alpha, where we are going to write VLM to be 440 times root 2 volts. This is 440 times root 2. That's what we said. So now let us try to write this as V load is going to be equal to 3 times 440 times root 2. So 3 times 440 times root 2 divided by pi cos alpha. This is going to be the load voltage. And we have the battery voltage. V battery minimum is going to be 275 volts. And V battery nominal or maximum is going to be 300 volts. So what we are looking at is V load minus V battery divided by whatever is the resistance, that is going to be limited to 15 ampere. So I should say 3 multiplied by 440 times root 2 divided by pi cos alpha minus 275. So this is divided by 2 ohm. That is going to be 15 ampere. This is the case corresponding to minimum battery voltage. The same thing if I try to write for maximum battery voltage, this will be 3 multiplied by 440 times root 2 divided by pi cos alpha dash minus 300 volts divided by 2 ohm. This will be equal to 15 ampere. So there are two cases. One will give me the firing angle corresponding to 275 volts. The other one will give me corresponding to 300 volts. So alpha and alpha dash I should be able to calculate. Okay. And that is actually coming out to be 59.1 degrees is corresponding to 275 volts. So that is going to be 59. Alpha comes out to be 59.1 degrees, whereas alpha dash comes out to be 56.25. So this is the range of alpha in which my rectifier can work so that the current is not exceeding this 15 amperes. So that we have solved for. So calculate the range of firing angle, that is 50 6 degrees and 59.1 degrees. So 56.25 degrees when we talk about, we are going to have 300 plus 15 times 2, which is 30 volts. So 300 volts plus 30 volts, which is 330 volts. That is corresponding to alpha dash. In the other case, it is 275 volts plus 30 volts, which is corresponding to 305 volts. That is actually alpha value. So this is 59.1 degrees, whereas this is going to be 56.25 degrees. And if you look at the load voltage waveform, this is load voltage. And if I am assuming the current is constant at 15 ampere, so probably I'm going to have the current which is 15 ampere like this. So this is going to be the I load. This is the load voltage. Now, when I look at the current, whenever 1, 6 and 1, 2 are conducting, I will have, let me probably erase this. I don't have to worry about this because I had already drawn the load voltage and A phase voltage as well. So if I say this is going to be omega t, we actually drew the load voltage to be something like, let us say, this is the A phase voltage. So this is VA, whereas my A phase current is actually going to start from here. So A phase current will start from here and it will continue until here. So this will be the A phase current. And for 60 degrees, it is going to keep mum. And from here, it is going to start again and it will continue like this. So this is going to be A phase current and this is going to be A phase voltage. So this is going to conduct for 120 degrees and for 60 degrees, it is going to keep quiet. And again, for 120 degrees, this is going to conduct like this. So this is the way we are going to have the current. And if I see that, what is the power delivered to the battery? That is going to be, if I say it's a 300 volts battery nominally, and 15 ampere is the current. So this is going to be 4,500 watts is the power delivered to the battery. But power delivered by the rectifier when alpha is equal to 59.1 degrees, that is going to be 305 multiplied by 15. So many watts. Whereas when alpha is equal to 56.25 degrees, under such a condition, it will be 330 volts multiplied by 15. So the power delivered will also be different when I have two different firing angles. This is the way it is going to be. Okay. So this kind of concludes our discussion on rectifiers. We had seen half-wave rectifier with diode. We had seen center-tapped rectifier with diode. We had seen full bridge rectifier in single-phase case as well as three-phase case with diodes. Then we had looked at SCR-based rectifier. First of all, half-wave rectifier. Then we had looked at fully controlled rectifier with SCR in single-phase case as well as three-phase case. We had looked at waveforms with R load, RL load, RLE load. I would urge you to do a bit of simulation so that you understand these concepts very clearly. I have eliminated completely semi-controlled case because we are not going to look at them much in battery charging, especially when we talk about electric vehicles for electric vehicle application. Okay, so we'll start with AC voltage controller in the next class. We'll see that only briefly. Then we would go into DC to DC converters. Okay.